Good morning, everybody. We are going to pivot a little bit from the financial mathematics this morning. We're still going to be sort of in the field of study. We're going to be talking about exponential functions, which are the functions that represent a lot of finance. But we're going to look more at the mechanics of these functions and more so what their graphs look like. Rather than focusing purely on the financial aspect of things today. So this is 8A. Let me make sure I'm in the right book. I believe it's in the orange book. So if you're someone who wants to follow along in there as well, you're welcome to. Yes, this is the orange book. I just had to make sure. So I'm going to put OB there. Okay, so when I use this word exponential function, all that Mr. Price is talking about here, this is mathese for it. It's a function where you've got a variable in the exponent. So like this function right here, where we've got that x right there, the variable you're used to seeing, the unknown quantity is the exponent. And so you've probably seen these before. So basically with an exponential function, you evaluate them the same ways you would anything. So like, for example, f of 6. Well, x got replaced with 6 there, so we're going to replace that x with 6 there. So f of 6 here is going to be 3 to the 6th power plus 5. I do not know what 3 to the 6th power is, but I'm sure that Mr. Price could use a calculator to find it. 3 to the 6th power. So that's going to be 729 plus 5. So 734 equals f of 6 here. And so I'm going to do two more real quick just to give us an idea, remind us of a couple of exponent properties. So f of 0 here, we're replacing that x with a 0. So what is something to the 0 power? So it turns out that something to the 0th power is 1. So if you're curious about why exactly that is, let me know, and I can definitely go over it. So f of 0 is 6 there, and the last one we'll do is negative 2 here. So get a reminder of these exponent properties. So as a reminder, the way that you evaluate a negative exponent is you have to bring the negative exponent to the denominator, and that will make it positive, or from the denominator to the numerator. So like 3 to the negative 2nd power is the same thing as 1 over 3 to the 2nd power. And again, if you're rusty on those exponent properties and you're like, wait, Mr. Price, why is that a thing? Please talk to me, let me know, and I can get you to a point where you understand it. I am very confident in my ability to do that. So we've got 1 over 3 squared. That's going to be 1 over 9 plus 5. Let's see. If I want to add these fractions, 9 over 9, that's going to be 45 ninths plus 1 ninth. That's going to be 46 ninths right there in good old fraction form. So hopefully that reviewed some exponent properties a little bit. Hopefully that refreshed you on the mechanics of a function. I know we haven't looked at one. And so again, kind of a way that you can check to see if a point is on a function, to check to whether it's see whether it's going to satisfy this function, is by substituting the point in and seeing if that makes your equation true. So for example here, if we want to determine whether this point right here, when x is 3, y is 9, satisfies the equation y equals 2 to the x plus 1, all that we would have to do is say, okay, well, when y is 9, does 9 equal 2 to the 3rd power plus 1? 2 to the 3rd power is 8 plus 1 equals 9. So that means 9 equals 9, and that works. So yes, 3, 9 satisfies the exponential equation y equals 2 to the x plus 1. I'm sure I didn't have to write all that out, but just to give us some clarity. So then the next thing that we're going to look at here is actually graphing these exponential functions, getting an idea of what these graphs look like. And so you can get a good picture for an exponential graph the same way that you can any graph, and just substituting x values in. So let's see. Well, let's start with 0. Well, 2 to the 0, anything to the 0 power is going to give me 1. So the coordinate I'm going to graph here is 0, 1. I'm going to put a point right there. 2 to the first power would be 2. So I'm going to graph 1, 2. 2 to the second power would be 4. So I'm going to graph 2, and then if I can count, 4. Let's see, 3 squared is 9. So 3, 1, 2, 3, 4, 5, 6, 7, 8, 9 right there. And let's do these negative ones. So 2 to the negative 1 equals 1 over 2 to the first. That's just 1/2. So the coordinate here is going to be -1, -half, or +1/2, excuse me, +1/2. 2 to the negative second power is going to be 1 over 2 squared, which is 1/4. So -2, 1/4 is that coordinate right there. 2 to the negative third is going to be 1 over 2 cubed, which is 1/8. And it's going to keep getting smaller and smaller and smaller and smaller. So I'm going to connect these points right here with the curve. And this is the general form for an exponential function. So a couple things I want you all to notice here. So this graph is going to keep going further and further left, but the y value going that way is just getting cut in half each time. So it'd be like, for 4, it'd be 1/16, 1/32, so on and so forth. And if you keep cutting something in half, you won't ever have a 0 amount. So there is basically a line here at y equals 0 that's like, hey, if you're cutting things in half, you'll never ever hit 0. There will always be a little bit of something. And so the default horizontal asymptote, if it's just something to an x power, is the equation y equals 0. It's not going to cross that line unless we shift it mathematically. And so it's the other notation right here. So this is just this is called in behavior. This is another way of just saying what direction is the graph going. So as y approaches, excuse me, as x approaches negative infinity, I want you to think to yourself, okay, what direction is that? If something is going to negative infinity, what direction is that on a graph? So this just says as x is going to the left, so what is y getting closer and closer to? So you can see as this graph gets further and further to the left, it is approaching 0. So this is just math talk for as the graph goes left, it approaches 0. That's how you would say that. That's just a more concise notation. Don't have to use all them words. Confucius said, "Why use many word when few word do trick?" I don't actually know if that was Confucius, so do not quote me on that. So here we've got x is greater than, or not x is greater than infinity, excuse me. As x is approaching infinity, as we go further to the right on this function, what are we approaching? So think to yourself, as we go to the right, what are we approaching there? Y is approaching infinity as well. So we can say as the graph goes right, it approaches infinity. And so that's a general idea for how we can look at the graphs of these exponential functions. So the last thing that we're going to look at today is actually looking at these graphs, like kind of getting an idea of how to sketch them without having to plot a bunch of points. So the general exponential functions will either be of this form: y equals k times a to the x plus c. And when you actually see it, the only things that won't be filled in are x and y. And then the only difference is occasionally that exponent can be negative. And so a couple of things. So like if your a value is greater than 1, you're usually going to be having a graph that is increasing. So like if it's 2 or 3 or 4 or 5, it's generally going to be increasing, and it'll be decreasing if you're repeatedly multiplying by a number between 0 and 1. Because whatever a is, that's what has the exponent on it. That's what you're going to be repeatedly multiplying by. So like if the number I was repeatedly multiplying by was 3, you would expect that graph to increase. If the number I was repeatedly multiplying by was 1/2, you would expect that graph to decrease. Now, see right here, whatever you're adding or subtracting by, that's going to cause either a vertical upward shift or a vertical downward shift, and that's going to affect where your horizontal asymptote is. So that whatever the value of c is, whatever's being added, the default is 0. C causes a vertical or a vertical shift up or down, and so C is always going to be your vertical or horizontal asymptote. When you're looking at the x values, if you've got a negative x value, so like from here to, like if you've got a negative x value, it's going to change the graph from increasing to decreasing. And then the sign of k is basically going to determine whether your graph is going to open upward or below the asymptote. And so basically to sketch a graph of an exponential, you're going to use the horizontal asymptote, the y-intercept, and 2 other points. And so as a reminder, that y-intercept is just found by making x 0. So we're going to look at 2 more graphs of this, and then we will call it a day. It's going to be a pretty short day today. So the first thing that we're going to look at the function y equals 2 to the negative x minus 3. And we want to get an idea of what this is going to look like. So the first thing, this minus 3 right here, this is going to determine the horizontal asymptote here. It's going to take our horizontal asymptote of y equals 0. It's going to move it down 3. So it's a horizontal asymptote of y equals negative 3. So already Mr. Price is going to start sketching. 1, 2, 3. We've got an imaginary boundary that this graph is not going to cross. And this is going to help us get an idea of what the sketch is going to look like. So then the next thing is we're going to go and we're going to get the y-intercept. So to get the y-intercept, on a y-intercept, if something crosses the y-axis, it has an x value of 0. So mathematically, to get it, what we're going to do is we're going to say 2 to the negative x. So we're going to say y equals 2 to the, we're going to plug in 0 to the negative 0, which is just 0, minus 3. 2 to the 0 is 1. 1 minus 3. So we're going to get a y value of negative 2. So our x, or not our x-intercept, excuse me, the y-intercept here is 0, negative 2. So I'm going to mark that point right there. And then we need 2 other points to get this graph. So let's see. One of the points that we can use here, let's use the x value. And Mr. Price can be sneaky here. So he sees that that exponent's negative. He likes positive exponents better. So he's going to substitute in a negative number to make it positive. So let's do x equals negative 1. So if I do y equals, that's going to make 2 to the first power minus 3. So then that's going to give me y equals -1. So the coordinate that I've got here is -1, -1. So let's see, -1, -1. And then the other coordinate, let's do x equals -2. So then let's see, so x equals -2, that's going to be y equals 2 squared minus 3. That's going to be y equals 4 minus 3, y equals 1. So my coordinate here is going to be -2, +1. And so this is enough information for me to get an idea of our graph. Because we know this graph is going to approach this horizontal asymptote, it's going to level off toward -3. And if it's leveling off this way, it's going to be shooting up this way. This is always the shape of an exponential function. And so then, the other thing that this wanted us to do is to state the domain and state the range. This stuff don't go away, y'all. We want to talk about what is acceptable to evaluate this function for. So the domain, as a reminder, that's the x values. The furthest left that this graph goes is -infinity. The furthest right that this graph goes is +infinity, and those infinities are not included. So then the range here, the lowest that this graph is going to get to, it's not going to cross this y equals -3 right here. It's going to get as close to it as possible, but not be included. So what we're going to do is we're going to put -3 with a parenthesis to say this is not included. And then the highest that this graph goes is up to infinity. So that is a general sketch of that exponential function. So let's get one more, and then we will call it a day today. One more, and we will call it a day today. So they didn't have enough examples for Mr. Price's liking, so we're just straight up going to do another problem from this book. So let's look at number 7 on page 189 here. And so what we're going to do is a 3-step problem. We're going to evaluate some points, help ourselves out a little bit, state the equation of the horizontal asymptote, and then we're going to graph that sucker. So let's see. The first thing we're going to do is evaluate. So we've got f of 0. I don't know why I wrote f of, these should be, I'm going to change this to an f now. That was improper notation by Mr. Price here. So we've got f of 0 is 3 times 1/2 to the 0 power plus 4. Well, anything to the 0 power is going to be 1. So we've got 3 times 1 plus 4 equals f of 0. So that means that our y-intercept here is going to be 7. So we got the coordinate 0, 7. From that, the next one we're going to do is 2. So let's see, f of 2 equals 3 times 1/2. That is squared plus 4. So let's see here. That's going to be 3 times, so 1/2 squared, it's going to be 1/4 plus 4 equals f of 2. So 3 times 1/4 is going to be 3/4 plus 4 equals f of 2. For those of y'all who are like, I need a calculator for this, don't you dare. 3/4, that is 3/4. Think to yourself how much 3/4 is. So that's going to be 4.75. And then our coordinate here is going to be 2, 3.75. So then the last one here, let me box that kind of weirdly. We've got f of 2 equals 3, this is -2, excuse me, 3 times 1/2 to the -2nd power here, plus 4. So what we're going to do is we're going to flip that fraction right here and make that a positive power. So that's going to be 3 times 1/2 squared plus 4 equals f of negative 2. That should be 2 over 1, excuse me. So that's just 2. So 2 squared is 4. 3 times 4, that's going to be 12. Plus 4 equals f of negative 2. And then that's going to add to 16. That's going to give me the coordinate negative 2 comma 16. So just a little bit of light coordinate work. So then the what we're going to look at now, okay, on B here, state the equation of that horizontal asymptote. So what is being added? How are we shifting this graph right here? We're adding 4 to it, which is going to move it up 4. So that horizontal asymptote is going to be y equals 4 right there. So then the last thing that we're going to do here is we're going to use all this information, sketch a little graph, and with that, so what I need y'all to understand, I do not need these sketches to be perfect. I know how some of you all are. You like for things to be perfect. I promise Mr. Price's feelings will not be hurt if I get a rough sketch. Y'all see the stuff that I'm drawing right here. Life will go on. Mr. Price will be okay. So we've got the coordinate 0, 7 right there. We've got the coordinate 2, 1, 2, 3.75. That should be 4.75. I don't know why he wrote 3. Come on, Mr. Price. 4.75, excuse me. Y'all probably caught that and were like, yo, Mr. Price, what's going on here? And then negative 216, that's going to be like way up here somewhere. You can tell these sketches are super precise. And I'm going to draw a curve through those. And that is a rough sketch. That's a rough sketch. Now, the domain here, because it did want us to do those two things, domain and the range. The domain, furthest left it goes left for forever. So we go negative infinity. The furthest right this thing goes, we can plug in any value for x here. Negative infinity to infinity. Again, just to emphasize, you may see this as all real numbers. That's what negative infinity to positive infinity means. And then the range here, the lowest that this thing can go is the y value of 4, but we're not going to include that. The asymptote doesn't allow us to. And then the highest this thing goes is infinity. So that, in a nutshell, is exponential functions for today. So if you all have any questions on exponential functions, please let me know. I do not mind to answer any questions that you all have. And I hope that you all have a good rest of your week and have a good weekend. Bye.